Welcome to the second lecture of single-cell RNA sequencing. In this case, we are going to use the R code. Follow this that single-cell sequencing analysis is a complex and advanced bioinformatics level thing. So you have to be patient to do the analysis. First of all, we are going to clean the environment and clean some RAM as well. So RAM is also being cleaned. I'm gonna clean it again. So 962 megabytes are available. So we are going to use this and then set the libraries. So here you are seeing I'm using the tidybus and the Seurat pipeline. So pipeline Seurat was built, yes. So Seurat is loaded, and after that we are going to use a single cell data to our single cell data folder and set the path there, and then list the gene and then the single cell. And then first of all, then we are going to import the file. So now that the file is being loaded, it's gonna take some time because we got the heavy file of which is saying that it used the 2000 megabytes file. So it is processing that file. So we are interested in the gene expression, and then first method is importing the data. Now we are importing the data. So take a look at your memory as well. Memory in use, it is using around 3580 megabytes at this time. When I first started, it was 900 and something. So it is taking a lot of memory as well because we are performing a high value and a high performance task. So let's just wait while it is loading the data. So we're gonna keep an eye when the data is loaded, and we are going to again get our cursor. So it is taking a lot of time as well. Then we can move to our second step, which is creating the Seurat object for our raw counts. So while we're waiting, we should have done this around. So it is taking a lot of memory. So let's wait while it loads the data. It is running down as well. So it's going to be done quite in some time. So okay, so it is just by loading the data, you can see it is taking a lot of time. So genome matrix has multiple while returning a list of matrices from this genome. So in our genome file, because I already told you it's going to take a lot of time. So I got the HV file which has the next gen biomarkers of raw features from our blood cancer. So it is establishing the genome file. So we are going to wait while it establish the genome file. Okay, now that our file is created, we can also see here that it has the gene expression, antibody capture, and multiplexing capture. So while we can open the gene expression file as well. So here you can see there are 3,600 and something genes like that. Here you can see all the genes are being loaded. I'm going to interpret that. I'm going to exit that interpret, or if it's gonna do so. So you R is not responding at your request to stop the current. You may need to terminate. Yes, you want to terminate the R. I'm going to terminate R. Okay, it is restarting now. Oh, I think we have to load it again. My computer has around 16 megabytes of RAM and around 2000 and stuff like that. So let's just okay, environment is killing. So let's load it again and move to our file. Now Seurat is being loaded, and our path is now created, and we are going to import the data. And here you can see we have the we are now importing the data. It is going to take a lot of time as well. So while we wait while the data is being loaded, and it is taking the memory again, and it is creating that values. So while it loads the data, we can look at the procedures that are defined here. First, we have to import the data file, that genome file that we take from 10x Genomics. After that, we are interested in gene expression data. I showed you the gene expression files. Then we are going to create the Seurat object, which is the raw count object that I told you earlier in my lecture as well. After that, we are going to perform the quality control and quality check to see that if the low counts gene are eradicated and are filtered out. Then we are going to filter the data around 2500 RNA-Seq, and after that we are going to normalize that factor. After normalizing, we are going to identify the highly variable features. And after that, we are going to identify some top 10 SVG, top 10 genes that are available in our genome. And after that, we are going to scale that. So now that our genome has been multiplexed, we are going to run the command of multiplexing and then getting the gene expression files. And then we are going to create the Seurat object. We wait while it now creates the Seurat object of counts of NCLS. So we have to wait to get our data. So it is saying that we have the gene expression formal DG matrix, antibody capture formal class DG matrix, and multiplexing captures of our data. So waiting while the Seurat object is created. So the object has been created. Let's move to the next step. Now we perform the quality control. And here you can see we got the and count data, feature data, and percentage data. And we can also see if the violin plot is now featured. While it's running the command, it shows us the featuring scatter of our plot. And there is no plot that is being reticulated now. Yeah, here you can see it has the plot was shown here, and then it got vanished quickly. So now we can see, yes, here we got the RNA count feature data, the RNA features counts data, and the highly variable thing that can be appeared here. Here you can see in the zoom in progress, here are all the genes that are presented here. It is the top NSCLC gene, and now close this and move on. Was our and this was the quality control check, and then we move to the filtering of genes. After filtering out, we're going to normalize these genes. Now it is performing the log normalization. It is done 100%, and then move on to identifying the high variable variants. So gene variants are being counted, and then the gene variables are being standardized, and clipped values are presented, and then the top 10 values will be given out to us. So while using the REPL, we can also define some. And so here we can see we got the average expression. So we are going to look on this if we got the average expression well. So here you can see we got the IGAP and a lot of variable count genes and non-variable count gene. Here you can see that. So here are the genes that are highly variable, and they are shown by their gene ID as well. So let's move on to scaling. So here we can centering and scaling the data matrix. We wait while the data is being centered and scaled out. Now the scaling is done 0%. So it is going to take a lot of time. So we wait while the analysis is being done, and I think I'm gonna move my Linux terminal. I exited my Linux terminal as well, so it can focus on itself. And it has used the 40,000 megabytes file as well. So it's going to take a lot of space as well. If your computer doesn't have that kind of space in it, so you can't run the single cell sequencing analysis on your R function. And I am going to give away this code. I think I shouldn't, but you can get this code from my GitHub account. You can use this to analyze your results because I think the code should be available to you so you can use it easily for your analysis. And if you guys want me to analyze your data and something like that, you can also approach me anywhere using my email, my website, which is Biodata Nerd, and my Instagram account, which is also Biodata Nerd, and my personal Instagram account as well, which is also available on the Udemy to discuss the bioinformatics techniques and things like that. So now we are waiting for the centering and scaling of data metrics. And the scaling top 10 genes are available here. Here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 10 top genes are available for the average expression, and now we are waiting for the centering and scaling of our data. Now it is operating the data and scaling. Okay. So it is performing at the 100%. So while we are waiting, you can also check what kind of plot this is. So when we are previously talking about, we were talking about the PCA analysis. So here you can see the next step is also the PCA, where we can determine the dimensionality of the data, and then we can create the clusters and then dim plot them, and by using the uniform approximation projection, we can create some data sets as well. We can create a cluster and then we can visualize that cluster. So we are going to wait while the single cell sequencing data analysis for the centering and scaling of data is being done. So that is taking a lot of time for us because single cell is not an easy and not an easy bioinformatics analysis. It takes a lot of space and memory to analyze the genes. So in our counts data, we have almost around 20,000 genes which we are now scaling, and it is taking a lot of time as well. So it is also using our 550 megabytes Windows source system as well. So while the scaling is being done, I think we should wait. Now I think it's rounding up because the memory is getting less and it is creating an object of a data matrix of scaling. So let's hope that it follows up in a few minutes as well. Also, you can save these plots. I forgot to tell you. You can right click on it and then save the image, and then use it further for your analysis as well. So here we were at our scaling process, and my computer and my laptop is already running at very high speed. It's using a lot of RAM as well and using a lot of my processing speed as well. So I think scaling is much more complex than loading the data and filtering it, I think so. Now it is taking a lot of less memory. The scaling of object is being done by using the UMAP technique. So now that scaling has done, we move on to viewing our single cell scRNA, and here we can see we got the counts data, acid data, meta features, and things like that. Now we move on to the PC analysis. So we use the variable features to plot the features and variable and feature references as well. And now we wait while the PCA features are being displayed, and then we can use these features to analyze our next data. So now that PCA analysis is being done, we are just two process behind to complete our single sequencing analysis. You can use this code from my GitHub account and then get it and then use any of your file to create your dataset and then use it for the single cell sequencing analysis. So now we wait while the RNA features for the PCA are now being exited, and it is now taking up a lot of time again for the PC analysis because genes are being clustered and they are scaled to their data matrices as well. Now you can see we got the analysis result. Here we are seeing the clusters are created, a positive, negative cluster for PCA1, then we have the cluster for PCA2. Here we can print out these clusters and then the map is now generated. So I was discussing these clusters PC1, PC2, PC3, PC4 and PC5. These are the 5 clusters that are generated here. You can see the PCA1 clusters of the genes are now represented here. And then we can move to the other plots as well. So the plots of all the PCA2 and PCA1 are now being compared. So now we can use the elbow plot as well. So here is the PC standard of all the standard deviation. Now we can move on to clustering and finding the neighbor. So here you can see we are computing the nearest neighbor graph for us, and let's wait while it does that. And now we have the nearest neighbor as well. So number of nodes we have 2485, and number of edges we have 78,762, something like that. So we are running some Levin algorithms to check out the edges and nodes and optimizing their genes count and count feature data. So let's wait while it's running up to 100%. So now we can view the data. So here you are seeing that we have the NCLC original identity, count data, feature data percentage, 1, 2, 3, 4, 5, 6, so many runs we have. So let's demo plot another one, and here we can see our sequencing PCA and SEC data. So let's zoom into this analysis, and here we can see the number of our genes, PCA, and things like this. And now we move to our identical, and then we can plot the UMAP as well. So writing the NN index to our file. So the file has been saved, and now we are allowing the call and connecting the KNN distance calibration with our target nearest neighbor. Now we are using the method of uniform manifold approximation projection to complete the task above 100%. And then we are also going to demi-plot it as well against our PCA. So by seeing this plot, you can project that these are the genes that are represented from 0 to 21, and the highest value containing are CA21 and the smallest is 0. So our optimization is finished. We can demi-plot our values by the form of clusters. Here you can see we got these 4 clusters, 5 clusters, 1, 2, 3, 4, 5 clusters. And then we can also save this as well. So it is going to save it in our directory, and let's just wait while it save all the files. So that was it for our whole single cell data analysis.